Okay.
Yeah.
Welcome everybody to the discussion session, which will be run by Maxime, who has invited some other people to speak as well. So go ahead, Maxime.
Okay, thank you. So that's the question is how to start this session. And it seems kind of natural. So this question of naturality to start kind of backwards in time, probably starting from Gordon, then me, and then Johanna, and because there are also people from other sections, from other days who may speak. For example, Ananda, Erica, and also Renee wanted also to talk. So it would be great, I think, better to give back in time. And I would like to say that this session is devoted to discussions about theory and experiments. So how can we get some non-trivial information from experiment using the theory, and particularly theory at the bulk. And I actually have a coffee machine at my office, and I have small plate here for coffee, for taking coffee, which I like very much. It's very good for, actually very suitable for our session. It's written here, it's written in French. It's written like un jour j'irai vivre en théorie parce qu'en théorie tout se passe bien. In English, this wish, one day I will be living in theory, because in theory everything works well. And in reality, of course, a little bit different. So the question is somehow to reconcile experiment and the theory. So probably we can ask first questions to Gordon and see what is his opinion about observation of the effects in the experimental framework.
Okay. So the things I talked about, the edge ferromagnetism and graphene, it is somehow notoriously hard to observe. The idea has been there for many years, even before graphene existed in the lab, and it's only very recently that some fairly sophisticated experiments, in fact, I didn't put a reference in my slides to it because I actually couldn't find the paper in my scramble to prepare the last few slides. But it's only fairly recently that there was a paper in Nature where they claimed to actually observe this, line of ferromagnetically aligned spins on a zigzag boundary of graphene. Part of this is because a really clean, long boundary is not that easy to make. So techniques have been perfected over time and are now pretty good. I don't remember how long the pieces are, but they're certainly macroscopic compared to the lattice scale. They're, at least micron lengths or maybe even longer. The armchair boundary has been explored less, simply because it doesn't have these edge states. And a lot of this exploration was in the context of ribbons. So, a finite piece of finite width, which for zigzag edges has these edge states on both sides, and there are interesting correlations across the ribbon because they interact with each other weakly, and that actually lifts the zero modes. They don't have exactly zero energy anymore. And that's been very interesting to condensed matter physicists, and they've studied it a lot. The armchair nanoribbon, on the other hand, has a gap in its spectrum, and it isn't as interesting for that reason. It's an insulator. You might be surprised that something of sort of macroscopic size or mesoscopic size already has a gap that would bother anybody. But that's because, unlike the Schrodinger Hamiltonian, where the splitting of energy levels just from geometry goes like 1 over width squared, for the Dirac operator it goes like 1 over width. It's linear. So this gap tends to be bigger in a mesoscopic system and is appreciable there, and people didn't study it as much for that reason. It just isn't as interesting for electronics. But that is the case where you actually have a CFT in the boundary CFT by definition of conformal field theory, because that's the case where the boundary condition doesn't violate the conformal symmetry. So from our point of view, that might even be the more interesting case. And I would think that if someone had something interesting to say about it, that could inspire a whole generation of experiments. And believe me, every university in the whole world seems to have a graphene lab because it's easy stuff to make. And so the things they do, just any new idea gets explored very vigorously. So this is something I would encourage people who like this subject, even from the theoretical side, to sort of think about seriously. I don't know if I have much else to say. This is a huge field, and of course, it's only a subfield of this sort of 20-year trend in condensed matter physics towards topological materials. So there are lots of other sort of examples of Dirac-like spectra here and there, and topological protection of things. And I think they've been talked about in this conference. Unfortunately, the conference for me is in the middle of the night, and I generally have things to do in the daytime. I'm not against being awake in the middle of the night, but if I also have things to do all day, it's a little bit difficult. So I haven't seen the talks. Maybe they'll be online and I'll have a look at them there, but I haven't done it yet. But there is a very big field out there, and particularly graphene is easy to make. Just about every nanoscience lab does it. Just about every university has a nanoscience lab, at least a small one. And so there are really a lot of people interested if you have something interesting to say. I think that's my point.
Christopher has a question.
Yeah, I've been kind of puzzled about the connections between these four components of the spinner and in these representations of graphene in the Lorentz group, because it seems kind of accidental that you get these four components, right? That it comes from the lattice structure. And in that context, is it really completely clear how to generalize the generators of the conformal group to include include these gamma matrices? Is that?
No, but I think you have to do it because you need the fact that that the spinor dynamics is governed by the Dirac Hamiltonian or the Dirac equation, and you need your transformation of the spinor to still obey the Dirac equation. So you actually just mathematically need these spin components. I sort of thought about that a little bit myself, and I don't see a way around actually including what they call pseudospin, but here it really looks like spin in the generators of the conformal group.
I mean, it's also been a kind of more general question to me too, in context of like Maxime's talk, where you want to include like magnetic interactions, and then we write down a QED with these kinds of fermions, and you couple the magnetic field to them. Again, it seems like you might get the wrong answer if you're not careful, right? That the magnetic field is coupling to the actual spin rather than the pseudo spin that you get from the lattice structure.
Well, it couples to both. And it couples much more strongly to the pseudo spin, actually, typically. In graphene, that's the case. The coupling, the Zeeman coupling is sort of down there in the noise at the millivolt level, depending on how strong the field is. But in all the breaking of valley symmetry and spin symmetry and so on, for example, in the quantum Hall systems, you see this symmetry breaking happen quite easily. And one could give a talk about that, except it's kind of an old subject by now. That never seems to be seeded by the Zeeman interaction. Somehow other things are more important. And you do see in that Hall effect picture, clearly the Landau levels, and they're Dirac Landau levels, and the Dirac nature of them comes from the coupling of the magnetic field to the pseudospin. So it's really important there, actually.
Okay, Andy, you wanted to talk?
Yeah. I was just naively, it looked like everything you did could generalize to higher dimensions. So my question was whether, in particular, the strange edge modes, are they special to 2+1, or could they be in other dimensions too?
This I don't know. I was just thinking about this while I was writing up the talk. Here, the edge modes come from this kind of funny zigzag boundary condition. And I was thinking, does that an analog of that boundary condition exist like one higher dimension? The other boundary condition, the armchair one, is actually the same as the MIT bag model boundary condition and sort of boundary conditions that are commonly used around it in problems with fermions. But the zigzag one's a little different, and I don't see why not. I mean, it looks like it, you know, you need alpha dot the normal vector, where alpha are the Dirac matrices, to anti-commute with your boundary condition. I don't see why you can't use beta there, or gamma 0. And I just haven't thought about what the pitfalls are. You know, maybe it violates some symmetries, but so what? You know, it's not a big deal. And beyond that, I think things would be rather similar. You'd have boundary conditions where, you know, the up or down components of the Dirac spinner vanish at the boundary, and you have to solve a Weyl equation. And I suppose there could easily be static solutions like that of a Weyl equation. It's just that it's my experience that it's easy to do wrong things in this business. So it requires quite a bit of thought to see if it's consistent. But yeah, I don't see why not, you know, as long as you are careful that everything actually works. You know, one thing I spent quite a bit of time sweating over is, you know, proving out a complete set of states, that there aren't yet some other modes somewhere. In the end, it's straightforward and easy, but, you know, it takes some time and so on. And I was worried you could be missing something. You know, you have the 0 modes. Maybe there's some other states somewhere, strange states that you know, participate and fix up all the problems. And the answer here seems to be no. Higher dimensions, I don't know. That's sort of an open issue, I'd say.
One other quick question is for the zigzag nano ribbon. Do you have any idea how you would see the opposite sides or pointing opposite ways from the continuum description?
I think so, because all you have to do is make a strip, right? Put your continuum theory on a strip. The 0 modes won't be exact 0 modes anymore. They'll have an energy splitting that's exponentially small in the width of the strip. So they're still almost 0 modes. And one thing that happens in all the mean field theory calculations, which I haven't addressed here, in fact, I was thinking about that too, is they seem to still be ferromagnetic, the edge states, but they orient on the two sides of the strip in opposite directions. And again, there are sort of different kinds of zigzag edges, right? Sort of, and so that's not a universal statement, I don't think. There are zigzag edges where the zigzag is offset. So, you know, top component of the spinner is 0 on one edge and bottom component on the other edge, say. And there, I think the physics is a little different, but they still have a small splitting in the energy, and you can see it quite easily and get fairly explicit solutions, you know, just in the continuum description.
Okay, thank you.
I thought Ananda wanted to ask a question, but probably it was already answered. So next, please, Rene, please.
Yeah, I think I want to pick up on what Andy just said and maybe phrase this into a question because I'm not completely sure. So if you go one dimension higher and you look at Weyl or Dirac semimetals, the interesting edge states that exist there are topologically protected. The Fermi arcs must be there for topological reasons. So in that sense, I mean, here the situation, I guess, Gordon, that's the question, is different, right? There's no topological protection for these edge states. and hence they can exist with one kind of, boundary and not with the other kind of boundary. While I guess in the whole zoo of Weil semi-metals, such a statement doesn't exist. There are Weil semi-metals with rather different lattice structure, and hence if you cleave them differently, the boundary lattice structure is also different, but the Fermi arcs always exist.
Yeah, that could be. It's true that if in the nanoribbon case, you get a splitting of the edge states, it means that there's at least the fact that they have zero energy doesn't seem to be protected by topology. But of course, a ribbon has a different topology than a half plane. So these things I'm not sure about. I'm never sure enough to say that something isn't protected, right? Because if it is protected, then you tend to know about it because you know the mechanism. If it isn't protected, you don't know that a mechanism doesn't exist for sure. I guess if perturbations change, maybe you can prove it isn't protected in some cases, but that's a more complicated question.
Yeah, I mean, it could also be that there is, usually these topological protections have to do with some kind of anomaly cancellation, right? Between the bulk and the boundary. And it could be that in both cases, there is some kind of anomaly that is canceled, but in one case by the edge mode, in the other case by the BCFT or something like this.
Yeah, I haven't really looked into that here. There is a parity anomaly for a single species of Dirac fermion in the bulk. I'm not sure it's really powerful enough to tell you what happens on the boundary, but again, I haven't thought about it very much, so I don't have a definite answer.
Yeah, thanks.
Can I interfere here? Okay, I should ask myself because I would like to make a comment here because you see everything depends on very small details, very tiny details, because indeed those you have armchair or zigzag and you have completely different types of modes. For example, you can consider modes which are thought to be topologically protected. For example, consider non-conducting medium, like say one slice, one layer tungsten ditelluride, which is one of the good examples of topological insulators, and it's good spin hole system with featuring in the theory featuring two modes, two helical modes counter-propagating. It's not Gordon's modes which are static as far as I understand, but those which are propagating. And then you can ask, okay, but let's take real thing, let's take real material, and right now let's cut it. And it turns out that the system is anisotropic in AB plane. In the plane, it's anisotropic. It has tungsten chains and it has perpendicular direction. And in both directions, you can do two types of cuts. You can do, like, say, armchair, it's a little bit different, and zigzag. The structure is a little bit different than graphene, but you can do two types of. So you have 4 conditions. And only for one condition, for one of those 4, you have massless edge modes. Others are gapped. So it means that they are massive. So no way for a single mode to go around this object. So it's everything depends on the details, very small details, and it's not easy to say it from very beginning. And then 3+1 is more complicated even because we can cut differently. Just a comment so that not so easy. But there we have an example when modes are totally this general bulk boundary correspondence in some real materials may not work, depends on the boundary, how exactly you cut it. It's in this particular. Okay, Ananda, could you please ask the question?
Yes, hi. So I think maybe you already addressed some of the questions, addressed this question somehow before, but I didn't really understand it. So, when you were discussing the edge modes, I was thinking about these works on fractional quantum Hall, where you could apply a gate voltage, and then you could see all these that you could see some boundary RG flows that you could have for transport with electrons transporting this current, and in a certain filling it seems to have it seems to quite accurately capture some of these boundary CFTs. So can we imagine doing something like that in these situations where we can induce some kind of RG flow in these systems?
It's a good question. The edge system if you just think of it as an isolated system, is not really a field theory because the modes are just static. They just sit there. You know, you just put it there and it doesn't move. So it's not a very close analog of the, you know, quantum Hall edge states, which are propagating. RG flow is, yeah, okay. It's something I've thought about quite a bit because, of course, I really like to make scale invariant states somehow. And of course, a scale invariant state you need a reason for making, and one reason might be it's, you know, something you would come to at the end of an RG flow. In other words, if I turn on a irrelevant interaction, somehow look at large distances, that interaction would prefer a state with which is scale invariant. In fact, that's what we find. I don't have a more detailed explanation for why we find it than that. It's just that this class of interactions we turned on happens to prefer such states. An actual RG flow, if you go from the lattice to the continuum, that's tricky because that's a very tricky one because these states have zero energy. So usually when you go from the lattice to the continuum, you assume that the energy of an excitation grows with this wave number. And so that, you know, short wavelength excitations also have very high energy, and you basically can integrate them out because they're not excited in low energy experiments. With the edge states I was talking about, that's not the case. The edge states on the lattice actually have no energy, but they have a whole array of wave numbers, you know, up to the wave numbers that I'm throwing away because they go to infinity in the continuum limit. And so the continuum limit for them is actually rather tricky. And I sort of figured out in the continuum how to deal with it a little bit. I had that discussion about the Hamiltonian and the charge density operator being able to you know, push you between graphene valleys because it could have very high momenta, and having to actually take that into account in the continuum theory to get an answer which matches the lattice. But I don't have a really good RG way of doing that, you know, of making an effective low energy theory, simply because these edge states happen at all wavelengths, right down to the lattice size. You know, wavelengths that I actually throw away when I go to the continuum theory. I don't have a systematic way of throwing them away or reinstating them. I do have a kind of rule of thumb about where I might need them or not. And that depends on the operators you're dealing with, how local they are in momentum space. If they're completely non-local, like a 4-point interaction in momentum space, then actually you might have to keep the influence of some of these states that you would otherwise throw out in the continuum limit. I don't have a systematic mathematical way of dealing with that, and I think that's what you're hinting at or asking if it exists, and I would say no, not yet.
Okay, thank you.
Yeah, Andy, please.
Oh, yeah, sorry for the double dipping, but I want to just clarify one thing, which was that in the end, with the zigzag boundary conditions, you had the dilatation symmetry again. So were those proper BCFTs?
No.
They were not, okay.
They're scale invariant, but not conformal invariant theory.
Okay.
And not Lorentz invariant, by the way.
Oh, okay. Sorry, what was breaking the Lorentz invariance? Was it?
The boundary condition is incompatible with the spin part of the Lorentz generator.
Okay.
Okay, since we have no more questions, thank you very much, Gordon. So probably then there should be questions to me because I was next speaker. If we go backwards in time. Yeah, please.
Okay, I looked again at this question during the break, which we were discussing earlier,
Yeah.
about this anomaly with the global and local term. So you have an anomaly contributing to the trace of the energy momentum tensor, which consists of, well, F squared basically. And okay, so what I checked is that the coefficient of this anomaly it's a bit special in QED because the fixed point is when the coupling vanishes. So in QCD it's different. Okay, so okay, it's in the UV, so it's for that reason it's different. So it's in our fixed point. But okay, so when the coupling vanishes, so in any case, the coefficient of this coupling is the beta function divided by the third power of the coupling.
Oh, no, that depends very much on normalization. That very much depends. Usually on E.
Wait, let me just try to finish. Okay, so the coefficient in front of the F squared term in the action is 1 over G squared if you choose that kind of normalization, okay? So this means, and the beta function to first order goes like E cubed, okay? So then if you take the Kayan-Semantic equation, then you have a derivative with respect to G, which then gives you a third power of G in the denominator, or E if you want, okay? And at first, in the one loop beta function, this just cancels the E cubed, okay? So, and then you just have a number. Okay. And this number is there also if the coupling vanishes. So you just first have to take this quotient of, I think it's 1 over 12 pi or something, E cubed, and then divided by E cubed. So then it's just 1 over 12 pi. And then you can take the limit of E going to 0, and you still have something non-zero even if the coupling is 0.
Okay, that's complicated. Yeah, okay.
Yeah, it would be very easy if I had somewhere to write.
Yeah, but I understand what you mean. The only problem that once.
Yeah, okay. So and then it doesn't matter whether you have a global or local symmetry. I mean, at first order, the coefficient is just 1 over 12 pi, and it doesn't matter.
Okay.
And in that sense, also the one loop coefficient is kind of universal because it's also there if the coupling is just 0.
Okay.
And then that confirms what you were saying about just the one loop result contributing. Okay, we have to see now what happens if these boundaries are present and so on. But I mean, that gives some support for what you were saying, that then the coefficient is the one loop coefficient is kind of universal. Okay, so yeah, but I think I think it's important to choose this normalization where the coupling just disappears from this quotient.
Okay, but then that's a tricky point. Let me just clarify here, because but that depends what you measure. You measure vector current or electric current, because for you I think they are the same. In reality, one should be multiplied. So if you take vector current multiplied by E, then it becomes electric current. You see, when you put E to 0, electric current vanishes. Full stop. You see, that's what I mean. So in that sense, electric current vanishes. On the other hand, if you take into account, so you consider axial currents and vector current, and in that sense, vector current is more legible, then you're right.
Yeah, okay, that's what I would have in mind. Okay.
Yeah, that one should be, that one can say that the answer is universal in that sense. Yeah, but in the experiment, they measure electric current, not vector current. And that's tiny difference, but yeah, but I agree.
Yeah, no, I understand. Yeah, okay, thanks.
Yeah, okay. Yeah, and then thank you. And other questions to the speaker? Yeah, I mean, from you, Johanna.
No, so for me, it's fine. I think you can pass on to Andy.
Okay. And then Andy, please. Yeah.
I had a short question and then a longer question. The short one was, well, again, it just looked like everything you're doing would work in higher dimensions or in any dimension. So is that true? Or did it depend on the dimension?
Yes, it depends on the dimension, because, for example, Gordon also found 1 over x in front of the current. In principle, he mentioned that he said that we have sigma xy, which is proportional to 1 over x, and that's 1 over x. It's exactly my 1 over x, which also I have shown. And it's similar things. Contrary to what he have shown, this 1 over x does not disappear when you consider full theory with all cones. So it stays there because it comes from normalization of the current. The point is that this is very tricky. This is very particular to 3+1. Okay, it's not very particular. I would say it's particular to the theory where we have a normalization of electric charge. So in principle, it could be in any theory, in any dimension. The only problem that if you want to consider really local theory, then by definition, you have to work in 3+1, because in any other dimension, you get a scale breaking in principle. If you consider electromagnetic interaction, you get then scale symmetry breaking because you have electric coupling, which depends on the scale, because it becomes dimension full. Like in, for example, 3-dimensional QED or 2+1, it has dimension square root of mass. In 1 dimension has dimension of mass. In that sense, you cannot speak about conformal symmetry from very beginning because it doesn't exist classically.
That actually leads to my next question was, what if instead of Maxwell, you had non-abelian gauge fields?
Oh, that you do everything with minus. Okay, that's that's complicated. In principle, it would be very interesting to see. The point is that this conformal anomaly, I mean, those currents, they kind of a little bit lose sense in the sense, okay, you don't have singlet, you have color current, and the conservation does not look like just a derivative, you know, it's this long derivative, and it's very difficult to give a sense to that. I tried to work with this, for example, in terms of the bug models, you know, for example, Gordon mentioned the MIT boundary conditions. You can do the same thing. You can put MIT boundary conditions and then consider, for example, fermions inside the bug and also gluons inside the bug, and you will have gluonic currents which will move around. It turns out that there is it's an interesting question to consider, as people usually say when they don't know sometimes what to say. That's a good question. So in this particular my case, I don't know what to say here because it's difficult to get consistent theory. So you get some current, but to give it any sense, it's difficult.
So you get a color, it would be a color current rather than
it will be colored current. Yes. It's not singlet, and the question is whether it gives, for example, contribution, for example, to spin of proton. You can say that there is something which is rotating. It should, in principle, should give some contribution to angular momentum, for example. But the current is colored.
Yeah, I was thinking of the quark gluon plasma because it's, you know, when it first forms, there's supposed to be a big magnetic field, and then if this effect is happening, you could get some. It might, like you're saying, though, yeah, you'd want to look for not the color current itself, but like some charge separation or something that you could actually measure. But okay.
One should think here not about actually a magnetic field, because magnetic field couples to electric charge and electric charge.
Color magnetic.
One should be color magnetic. Color magnetic, it can be understood in terms of that plasma, you know, kind of you have plasma, you have color electric fields, magnetic fields that somehow rotating. But then there is this question whether how to give this, you know, how to give sense to that current, whether it contributes, for example, to color invariant objects like angular momentum, for example. I don't know. It's a good question. Yeah.
Oh, and also, have people seen? I'm assuming they have, but have people looked at it holographically?
No. Oh, no. Okay. Yes. Okay. It depends on the context. In the context of, for example, Chu Miao, I mentioned two people, Chu Miao, who from Taiwan, and they did it holographically in parallel. So in my talk, I cited them. It was like 2 years or 3 years ago. They rediscovered what McCavity Osborne did 35 years ago. They of course cited them, but they first found that this answer is in a sense universal, in that sense that McCavity and Osborne considered some very particular case of boundary conditions, and they did not realize, as far as I understand, they didn't realize that it's beta function. And Chu Miao thought that it's beta function, and it doesn't depend on the condition. They can put Dirichlet, Neumann, and also I think at MIT for fermions. So it doesn't matter. So it's a universal thing. Yeah.
Okay. So okay, thanks.
Yeah. Yeah. And any other questions? Okay, now we can then pass to Johanna.
Maybe
yeah, let me just say, really, I was just going to say, I know René has prepared some slides and it's getting late, so maybe he should show them now. I mean, you know.
Yeah, it depends if you want me to go first, it's fine, but I'm very happy to do so, yeah.
Yeah, go ahead. I think it's more connected to what
Yeah, but let me first say something before I start with this. Let me say something about your question, Johanna, about the scheme dependence, because I'm really puzzled about this. So if you think of this as a high energy physicist, right, you always think you can choose any renormalization scheme that you want as long as the symmetries are preserved. But in a real material, in fact, the band structure is compact and it picks you out a particular renormalization scheme by the microscopics, in my opinion. So for example, I mean, so what I want to say is, like, if you go from, looking at this from the point of view of low energy theory, and then you want to fix your UV scheme, you need to put some conditions that it's actually compatible with the material that you're looking at, I think. So for example, in this paper with Evelina, where we looked at the anomalous wall conductivity, right? So there it turns out that the UV terms become very important, and you cannot just choose any UV renormalization scheme. Otherwise, you shift, for example, your anomalous wall conductivity. What do you have any idea about this?
You ask Johanna or me?
Anybody. I mean, because I was puzzled about this before when Johanna asked about the beta function, right? So the higher orders, like, are they really arbitrary? Like, from the high energy point of view, they are, because they're scheme dependent. But in your particular material that you take there, are they not fixed by in fact by the band structure that is actually UV complete by itself?
Maybe I'm too QFT minded, but I can't see. I mean, these things are really unphysical. So how could any band structure with this really physical fix anything?
Well, the band structure by itself is UV complete, right? It's compact. All states are there. And if you want to go beyond that, then you will destroy your crystal, right? The band structure itself, the Bredon zone is compact, right? So, and so I could in principle take T mu mu and calculate the expectation value just by summing over the whole band structure, and I get a finite answer.
Yeah, but the scheme dependence arises also in the finite contributions to the beta function, not just the UV divergence. So I don't see how this could work. Okay.
Yeah, exactly. But I just don't see, if you just calculate this it's a finite quantum system in a sense, right? If you just calculate this in this band structure, you get an answer. There's no, there's nothing to shift around anymore. There's no obvious scheme dependence there anymore.
I'm not sure.
Maybe we can discuss this some other time, but yeah.
You see, my answer is the following, just very simple. I already said it, but let me just repeat. I take first principle calculation, calculate and see non-trivial result. That's all. So it's there. So
yeah,
that's what we did. In principle, one can do, like in graphene, for example, we can do tight binding. And for example, it's also common to Gordon. During his talk, I also looked to literature. There is also nice work from Würzburg group, by the way, and they made, and also from Marseille, they made the first principal quantum Monte Carlo of graphene, of large graphene with some substantial number of ions. It's Maximo Libashov and others, and they found that they see the normalization non-perturbatively, and this normalization, as far as I see, it's logarithmic, so it's predicted qualitatively is predicted by perturbation theory. The only problem that the coefficient, I don't know, they did not compare with perturbative results. So they see some looks like logarithmic, so it's like perturbation theory. I mean, I speak right now about graphene, about normalization of velocity in graphene, which is becoming explosive in the infrared limit. So they found it, but I think they sent it to Nature Physics, I think, or Nature, because format is compact. Then they have huge number of supplementary material. It was totally understandable whether they say yes or no with respect to perturbation theory. So if this is correct or not. But functional form is logarithmic as predicted by perturbation.
So which paper is this again?
It's in April. It's in April. I can send just let me say it. Let me send it right now. If I send correct paper, I will send it over Zoom in the chat. Let me see in the chat to everyone. I will send it right now. This paper. Yeah, this is. I sent it to PDF. It was 19th of April, not 1st of April, 19th of April. So it should be serious paper. Würzburg, Frankfurt am Main.
Okay.
Yeah. So it's serious people. So I mean, we should believe. But yes or no is not actually. You can look at this at the last page. I mean, not last page, last at 14th page. It has 55 pages, but last page is basically 14 page. First sentence, they say that extrapolated logarithmic plot of quantum Monte Carlo data shows excellent agreement with experiment. So logarithm seems to be working. So, but it's maybe not being perturbation theory, something else.
Okay, so I don't know, maybe I should share my screen and just, okay. All right, so when let me share the screen. So I hope this works now. So no, now you can see the other one, yeah. So okay. So I think I first have to do the presenter mode, and then I share the screen. Weird, it's not working. Seems I haven't done this for a while.
Yeah, that happens.
No, there is something you have to do. You have to first, yeah, I guess yeah, so what you have to do is you have to first share the right screen and then it all falls in place. And how does this work again? Okay, let me try to share the other one.
Oh, you want to talk about all that?
No, this is just my, huge amount of screenshots from different talks and stuff. Okay, great. So now you're still not seeing the.
No, that was right. We were seeing the slides.
You were seeing the slides. Now do you still see them?
No, now we see you.
Sorry, sorry. Okay, so that was correct. Okay, so I was. Okay, I see. Now where's my Zoom window again? Here. I guess it's time we go back to in-person meetings. Okay, so now you can see my slides?
Yes.
Okay, great. Good. So yeah, thanks again, Maxime, for the kind invitation to talk in this discussion session. So when I read like the title of this conference, I thought, okay, what could I talk about that is related to boundary effects and so on. And so we have been working on electron hydrodynamics for some time, me and Johanna and the group, and also Evelina, for example, yeah. And so I thought I might just want to point out something that to some of you might be new, to some of you might be obvious, namely that boundary effects are actually very important in hydrodynamics in general, and in particular in these electron hydrodynamics experiments. Okay, so just to remind you quickly, so if hydrodynamics is theory of fluids, and everybody knows what's going on. You have a conservation equations, the Navier-Stokes equations, and they tell you how your fluid flows once it is locally in thermal equilibrium. But in order to get to that equilibrium, you first need to equilibrate the system. And if you want to do this in a solid state system, then typically this happens through Coulomb interactions. So basically you have your electrons in your system, you're at finite density, the electrons Coulomb interact, they exchange energy and momentum, and they reach local thermal equilibrium, okay? And if they do this fast enough, namely faster than any other process that makes them lose energy or momentum to phonons, impurities, etc., or to the boundaries, then you're in this electron hydrodynamics regime here. So the electron mean free path is basically shorter than all the other relevant mean free paths, and also geometric sizes of your sample, and then you can develop hydrodynamic electron flow. And so this can be achieved in several materials, for example in graphene. And typically you do this in a finite sample, obviously, and then the boundary conditions become important. And that's what I want to point out here. So if you, for example, have like a channel here, this is a sketch of like a two-dimensional channel, and you have like very rough boundaries so that your fluid cannot flow there at the boundaries. So basically the boundary velocity is 0. Then you get a non-trivial hydrodynamic flow in the middle, the so-called Poisson flow, where you get like develop in the non-relativistic limit, you develop this quadratic velocity profile here, okay? And so in fact, this has been observed. There are imaging experiments here by the group of Amir Yacobi at Harvard, for example. This is in fact in graphene here. So basically they measure the local electric potential here, and then through the Stokes equations, they can go back to the velocity flow, okay? So boundary effects are really important here. In fact, if you don't have rough boundaries, if you have momentum conserving boundaries here, then you cannot distinguish a hydrodynamic fluid flow from a non-hydrodynamic ballistic flow. Yeah, so then everything is just limited by the impurities, the momentum relaxing impurities that you have in your system. Okay, good. So what are these boundary conditions that people usually look at? I think that's also interesting in this regard. So there's this very nice paper here by Shmalian and Kiselev from a couple of years ago, where they actually microscopically derived the boundary conditions that you put in on such a graphene sample. And what you find out is that there is a whole one parameter family of boundary conditions there that interpolates from between so-called no slip boundary conditions here. Yeah, so there's like no velocity at the boundary, so the drift velocity is 0, to no stress boundary conditions where the boundaries are just smooth. I mean, they do not relax momentum, and there's no diminishing in the velocity profile due to the boundary. Okay, so and in the middle you can have some kind of interpolating situation here, which is given by the so-called slip length. Yeah, so the slip length tells you if you have your velocity profile here and you go out of your sample and you basically linearly extrapolate down to 0 velocity, where do you end up? Yeah, so if the slip length is 0, then your velocity goes to 0 by itself. Yeah? So then this theta is 0, and this the boundary condition here tells you that this tangential drift velocity just has to vanish. And if the slip length is infinity, then you're in this situation here where you just hit the boundary with 0 slope. Okay, so there's a whole one parameter family of boundary conditions here, and yeah, and so this is the generic situation that you can come up with. I guess one question that I had in view of this conference is, are there any special requirements of for these boundary conditions if you basically assume that your fluid here is that you have a bulk fluid that is conformal, and then you might have a boundary fluid, not just like a rough boundary, whatever type, you have a boundary CFT, and that's also conformal, and they're also conformally coupled. Yeah, so then you might imagine that these not all of these situations are actually realized. Yeah, yeah. So nevertheless, you see that the presence of non-trivial boundary conditions are important in this hydrodynamic fluid flow. And yeah, so and also in another setup we looked at this. Yeah, so we looked at these channel flows in the presence of a magnetic field some time ago with our colleague Evelina Hankiewicz and a student of her, Christian Tutschku, who is not in Würzburg anymore. He graduated, and yeah, with a postdoc, David Rodriguez Fernandez, and a PhD student who now also graduated, Yanis Matriakakis. And so what we did here in this work, we switched on a magnetic field in this channel setup here. Yeah, so this is now not graphene, but this is a non-relativistic setup. And if you switch on a magnetic field, you actually make the electrons collectively develop a Hall viscosity. Yeah, so this Hall viscosity is this non-dissipative time reversal breaking viscosity tensor that you can write down in 2+1 dimensions. And this whole viscosity, in fact, leads to an additional force perpendicular to this fluid. And if you go ahead, and here's where the boundary conditions again play a role, if you take the same boundary conditions that Gordon was talking about a second ago, namely there's no current that can flow out here, so these are kind of impenetrable walls, then you build up an additional Hall voltage across the channel that's necessary to basically cancel this force. Yeah. And so we did this, and we found, in fact, that this Hall voltage, that comes from the Hall viscosity can actually cancel the ordinary Hall voltage from the Lorentz force. So there's some cancellation point in magnetic field. This is the total Hall voltage drop here. There's some cancellation point where these two contributions cancel each other, and so you see that this cancellation happens basically because we allow this, by our choice of boundary conditions, we allow this voltage to build up. If you would have boundary conditions where you can have outflow, then the situation would be very different. So this is something that we did some time ago, and so here's my my summary, basically some food for thought. So as I just said, boundary conditions are actually really important in hydrodynamics, and I just I guess I want to point out two things here. First of all, as I already said before, like so if you actually have a boundary CFT setup, is there some non-trivial interplay between a thermalized bulk CFT and a thermalized boundary CFT that would kind of restrict the allowed boundary conditions there, and also in view of anomaly cancellation. And another thing that I think is interesting to think about in terms of ADS CFT is basically, so in ADS CFT, we have these strongly interacting fluids, and what I just showed you before was a weakly interacting fluid. So the question is, how can we actually distinguish these two situations? So can we, this is something, maybe one needs to take some special geometries that kind of make the whole fluid flow special boundary conditions that make the fluid flow very sensitive to the value of eta over S, for example. Or maybe one can look at the onset of turbulence. In fact, this is what we did in a paper from last year with Johanna and our condensed matter colleagues in Würzburg. So there we basically, we basically proposed a material that is more Coulomb interacting than graphene, and so this basically eta over S, the ratio of shear viscosity over entropy density is smaller, and so you get closer to the regime where you can actually expect turbulence. So this is also some place where one could look in experimentally distinguishing strongly from weakly interacting fluids. So these are 2 points that I basically wanted to make, basically in order to stimulate a discussion.
Okay, so thank you very much for the talk. It's short, quite good, and all information is here. Does anybody have questions?
Yeah, just to clarify, because I think I missed something. So you had, how did you get the Hall viscosity?
You get, that's why, because I skipped that slide. So so you get the Hall viscosity in an ordinary two-dimensional electron gas. These are non-relativistic electrons, by switching on a magnetic field. So this is basically work by Alexeyev here from 2016. What's happening is, if the electrons themselves already form a fluid at zero magnetic field, then you can look at basically you can look at the influence of the magnetic field, and you find out that Hall viscosity is generated that's proportional for a weak magnetic field is proportional to the magnetic field itself. So this is the cyclotron frequency, and that's linear in B.
But then was the statement that in the presence of a boundary, you would somehow have an opposite sign to the normal?
Yes.
How did you get the cancellation?
Yes. So whenever you have such a Hall viscosity, you know, and you have this kind of fluid flow. Basically, you have this quadratic fluid flow. You can look at the transverse part of the Navier-Stokes equation here, and you find this additional viscous Hall viscous shear force here, and that turns out to have the opposite sign as the ordinary Lorentz force.
Also, maybe I missed, but are there some edge modes that are?
No, there are no edge modes here, basically. So this situation here is completely determined. The edges are determined by this one number, by the slip length. Yeah, by the boundary condition that I choose.
So this is canceling just the classical Hall?
Yeah.
Very interesting, actually, indeed. So you mean that in fact you can cancel indeed classical Hall, so that you apply a magnetic field, and then depending on the boundary conditions, you generate opposite flow, and that's why you have zero voltage drop across the channel, right?
Yeah, that's true. Yeah, I mean, but I have to say, I mean, here we assume that we are completely in the hydrodynamic regime, right? So this cancellation, surely, if you, let's say, if you have some ballistic electrons zipping around in your channel, this cancellation might not be completely perfect, but you might actually expect a kind of a significant drop of some sort. Yeah.
Okay, very interesting. I want to have a comment. You said about turbulence, but as far as I know, that in graphene, you can hardly get high Reynolds numbers. So it's typically, say, one layer or double layer, you have like, I don't know, at least one, and most one, but turbulence sets, it's per turbulence sets at approximately 50, 40 you need to have. So you have to have huge, clean graphene sheets. Also, it's right now it's possible with huge holes inside, and it's quite, or how huge, you know, these constrictions inside, and it's complicated. So I know that people, for example, what they do, they sometimes, you know, put a big voltage drop, and they basically accelerate electrons along that, but then they have huge also joule heating, you know, the graphene heats, and that temperature increases and goes almost to room temperature, even you start from low temperature. So it's kind of complicated. There is one work by Polini, I remember it quite recently, okay, like 2 years ago, he studied kind of graphene flow in kind of constriction. So he puts bigger voltage drop and then closes channel, and then graphene just goes out with high velocity. But still, it's I'm not sure you can get high. How can you get high Reynolds numbers to get?
Well, I mean, one way. So in graphene, I agree that it's very hard. So people have. Let me try to find the relevant slide. So So this is the relevant slide. So I mean, I don't want to like spend too much time here. So basically, the first paper that I know about that investigates turbulence in graphene, in hydrodynamic flows in graphene is this paper by Mendoza et al. And what they do is, as you said, they make this is a numerical simulation. They make a constriction and they try to push the fluid through by an electric field and see how high Reynolds numbers they can get. And what they find is that they can actually only get so-called pre-turbulence. So there's this vortex shedding happening, but it's not a fully turbulent flow. And that's basically because the Reynolds number is not high enough. So even in this rather sharp constriction. So what you can do is either you increase the fluid flow velocity to get to higher Reynolds numbers, or you try to decrease the viscosity, right? Because if you decrease the viscosity, the fluid flow is going to become more turbulent. And so here is this formula comes from our paper here. So this is the Reynolds number estimate for such a channel flow, and so you see it's inversely proportional to 1 over eta over s. And so if you make eta over s smaller, you will make the Reynolds number higher. And there is also this factor of the typical velocity, which also depends on eta over s. There's like the max velocity here in this Poisson flow. Okay, and so that also, if eta over s becomes smaller, the max velocities become bigger. And so you also increase the Reynolds number, right? So at the end, the question is, well, how large is your eta over s for your fluid? And you know, if you believe the theoretical estimates for graphene is just not large enough, okay? So what you can actually do is you can think about, you know, maybe we can have some other materials that have stronger Coulomb interactions between the electrons which makes the viscosity go down. Yeah, and so this is what we basically proposed in this paper here. We proposed a material that has a higher Coulomb interaction between the electrons than graphene, about 3 times higher. So this is basically so we call this scandium Herbert-Smithite. So it's taking Herbert-Smithite, which is kind of a Kagome lattice layered material. And then you in Herbert-Smithite you replace zinc by scandium, and then you get to some material that where you can calculate the effective fine structure constant. Turns out to be larger than in graphene by a factor of roughly 3, depending on the input parameters. And in this way, you can increase the Reynolds number at the end. Yeah, but I have to say, so this material is a theoretical proposal, so this doesn't exist yet in the lab. So people have not been able to cook this set yet. So yeah, but yeah. So what paper by Polini are you talking about?
Yeah, there is a paper. Yeah, Polini published a paper 2 years ago, I think 2 years ago, on that. In graphene also, it's also numerical. But it's Boltzmann approach. It's not. It's not Navier-Stokes. It's Boltzmann. It's Boltzmann with, I mean, real Boltzmann in the sense. It's complicated, but they see. But it was later than the paper which you mentioned.
So it's also theoretical. It's theoretical.
Yeah, theoretical.
Okay,
I know it's in Belair. Maybe it's better, but yeah.
Yeah. So no. So as far as I understand, there is no experimental evidence for turbulence in graphene. Yeah, and the viscosity is just too high. Yeah.
Okay, thank you very much for the nice talk. It's very interesting. Maybe somebody also has a question, comment, because I have a few, but maybe we can talk privately because it's not a boundary. It's a boundary workshop, so probably one should ask some. Maybe we can talk later together. Okay, thank you very much for the nice talk. And actually, next speaker, I asked Erika Bertolini, who gave a very nice poster about the edge modes at the Chern-Simons systems and how the velocity of those edge modes depend on the gravity in the bulk. So it seems to be very pertinent to what we discussed, and it may be also observed experimentally. So Erika, please.
Yeah, I'll try to share my screen. Can you hear me?
Yeah, we see or hear you. Yeah. Okay.
Okay. I'll try to share my slides. Okay, can you see it?
Yes, we see everything, yes.
Okay, so yes, as you said, Maxime, I presented a poster on Monday, and it is based on a work with Nicola Maggiore. And well, I will shortly present just a small overview of this. So what we studied was the Chern-Simons theory in interior space-time and with a boundary. So the question we posed was what were the two-dimensional induced theory, and if the induced metric had any role in the observables of the boundary theory. So just making the long story short, the answers were that the two-dimensional boundary theory were a Luttinger model for accelerated chiral bosons on the boundary. So in a sense, it's like the flat spacetime case, it's chiral bosons, but this time the metric is involved in an observable, which is the chiral velocity of the boson. And well, the difference is in the known case, it's usually studied the Chern-Simons theory in flat spacetime, and a constant chiral velocity is observed. Well, in this case, so considering the curved spacetime and the curved boundary, the interesting thing was exactly the presence of the metric inside the the chiral velocity, which induced a time dependence on that velocity. So there is the possibility, in considering Q spacetime, to have accelerated chiral bosons. And so since this talk was more about experiments, well, the velocity is a phenomenological parameters, and in this way, by measuring it, possibility is to probe in a certain way the Kerr space-time by observing the acceleration of the velocity. But also other ways are, well, experimentally, I'm not exactly an expert in this context, but what I know, it has been observed in this paper in 2013 by Bukuyan et al. That by coupling two channels in a spinel system, and by making them interact, they observed accelerated velocities, and they made an hypothesis about dissipation, but they left the question open, and this could be an answer. It is possibility of Kerr spacetime, an effect of Kerr spacetime, and this is mostly it. Well, something interesting might be studying some kind of geometry, some geometries in the boundary conditions of the theory, by considering the parameters. But well, the how, maybe it's just more my question to all of you, maybe. And well, I think that is really interesting, since no one ever talk about an accelerated Kerr velocity, for what I know, mostly considering Kerr spacetime, well, as a consequence of a Kerr spacetime. If you're interested, I have some computations, some more details. If you have questions, I can explain more details.
Okay, Andy, please, you're first. Yeah, please. Thank you for the talk.
Hello, I saw your posters, so I've seen some of the calculations. But anyway, don't these edge modes have an equivalent description in terms of chiral fermions, and then you can bosonize them to turn them into?
Yeah. It is. We studied the bosonized version, in the sense that we defined the theory in terms of bosons, since we observed that in our model the degrees of freedom were scalar fields are bosons, but we can fermionize the theory
what would the this acceleration, or this metric dependent velocity look like in the chiral fermion description?
Well, I don't know yet. It's just something we have to do yet. Yes,
okay.
It's just
for the experiments. So would the relevant thing be like a quantum Hall system, and then somehow introducing curvature or something?
Yeah, it's something related to quantum Hall. Yes, I'm not exactly sure on how it can be done experimentally. That's my problem mostly, and that's why I'm asking this question. Yes.
Okay, those are my questions.
Renee, please. Thank you for the question. Yeah.
Sorry. I don't know. I mean, this velocity, is it maybe observable in the AC Hall response? I mean, if you would calculate the AC Hall response, maybe the velocity enters.
I think yes. I'm not sure I have the answer.
I mean, in the usual Hall conductivity doesn't enter, right? That's quantized. It's given by your Chern-Simons level. So maybe if you start wriggling the system in a time-dependent way, like in the AC response, maybe then it shows up. I don't know.
Okay,
Maybe.
we may try that. Yes.
So since this velocity also shows up in ordinary flat space, right? If you look at a quantum Hall sample, so the answer should be in every textbook on quantum Hall physics, I guess.
You're speaking about accelerated velocity. I'm not sure.
This velocity of the edge modes also shows up in ordinary flat space, yeah. So whether this shows up or not in the AC response should be in every textbook on quantum Hall physics, I guess. Maybe I would think, yeah.
Okay.
Yeah. But I would guess, sorry, so you're saying the Hall conductivity depends on like VF.
The higher orders in frequency, maybe, yeah.
So is this velocity like diffeomorphism invariant? I mean, if it depends on this metric, it doesn't naively look like it's diffeomorphism invariant.
Sorry?
So if this velocity depends on the determinant of the metric, then it doesn't look like it's diffeomorphism invariant. So what if I change coordinates? Do I get a different velocity?
Yes, but that's due to the boundary physics. Yes, boundary breaks diffeomorphism.
Okay. So would that mean that like physical quantities should only depend on, they should only depend on diffeomorphism invariant things, right? So, or is that saying something more like you've broken, like you have some impurities or something? Or?
Well, it may depend on the frame we're seeing. So lab frame.
Okay.
That was also actually, Andy, you also asked something which I also wanted to ask. In fact, in a quantum Hall, if you consider, for example, spin quantum Halls, okay, I'm not sure. Spin quantum Hall here, I think, is not applied because I'm not sure if the spin quantum Hall systems can get the same response. I'm not really sure because it's typical system with Chern-Simons, and probably it's better for Chern insulators.
Would that be would that be non-abelian Chern-Simons?
Could be.
SU2.
Yeah, maybe SU2, yeah. I don't know. So in fact, yeah.
No.
So what kind of system that could be exactly with this action one? It's Chern-Simons with the radial Chern-Simons bulk. It's what would be just quantum Hall system, right?
It's just a fractional quantum Hall system, yes.
Mm-hmm. Okay.
Yeah, well, what I think it may be a spin-Hall system, it's a BF model. That is.
Yeah. If it's a spin Hall system, then it's it works well. The point is that with those spin Hall systems, it's nice that in principle you can see edge modes. So you can see in the sense that you can consider response of the theory. Okay, that's I'm talking right now about topological insulators. Maybe it's not correct system. Okay, I'm not sure. So if you work with topological insulators, then in principle you can see modes because you can probe how they're conducting. So if they are kind of, if they even short, for example, you can assume that they are segmented, so you don't have really big transport, but still they're conducting locally, and you can see that experiment. And as Andy correctly said, that conductivity must depend on the velocity. So in principle, if you just say how there's a spin Hall, and then you just a little bit, just deform it with some pencil, basically, then boundary should change. Boundary's velocity should change, and then you should get, even without AC, even DC, but it should be static. You can get a different conductivity at the boundary then, just because you deform the bulk, and then conductivity of the boundary will change, and it will be better seen, really seen, in experiment. And as far as I know, in graphene, they did something like that, but not at the boundaries, but in the bulk. So if you deform graphene, then you get strong magnetic field. It was different effect, but they can really deform it, so they can have Gaussian profiles in the middle. So yeah, it's
changing the metric.
Yes, in principle, you can change conductivity, and conductivity can be seen. So it cannot be measured because, as I said, that spin coherence length is very short, but it can be seen kind of, you see if the thing is conducting or not and how good is conducting. So you cannot directly measure, but you can see from response, you can see how it's reflecting basically waves. Yeah. Okay, very interesting.
Thanks.
Does anybody, are there any questions in the audience? Maybe somebody wants to add something to the discussion. Yeah, Gordon, please. Yeah, you're yeah. I thought asking.
Actually,
Yeah.
in this, still in this subject, the curvature you're talking about, is it real space-time curvature necessarily, or can it be something emergent, like, you know, some geometry of the material or the boundary?
It may be some kind of distance in the material. Yeah. Somehow a way to define the material. Yes, it could be. Could be, yes.
And also the velocity of the charge carrier, in a sense, depends on the geometry. Do you know if the coupling, in a sense, the contribution of the charge of the carrier to the current, there could conceivably be a compensating factor there? Have you looked into that?
No, I'm not sure. No.
Because an electromagnetic field will have to couple to this thing in order for it to actually be an electric current, in a sense.
Yes.
So there should be a constant in that coupling too.
We haven't started that. No. I'm not
Thank
sure.
you.
Good.
Okay. So if you have no more questions or comments or propositions to talk, we kind of, yeah.
I'll stop sharing.
Yes. So we are in time. So we are just in time. So probably it's the best time to thank all organizers for this wonderful workshop. And really very nicely done, and it's very nicely organized. Yeah. Just we should clap for this for this really good workshop, and yeah, mutual discussions. Actually, those long discussion sessions, because they promote interaction between participants and make the chains between us and some links which will last for some long time. So thank you very much, Andy. Thank you.
Thank you. And on behalf of all the organizers, thanks for coming, and thanks to all the speakers for giving excellent talks. And most of all, thanks to the MITP for all their support and help doing this. Thanks, everybody.
Yeah, thanks a lot. Thanks to you, Andy, as well. And thanks to Maxime for organizing the session. That was also very nice.
Yeah, but it's Andy who's Andy organized, and also Christopher organized, and others. I mean, it's I was just serving this.
Great. Also, on behalf of the MITP, I would like to thank you to organize this lovely workshop. I hope you had a good time, and I hope we'll see you soon in person.
Yes, we very much would like to come to Mainz very soon. Yes.
We too.
Yeah.
Thanks, everybody. Yeah.
Thank you.
Bye.
Bye-bye. Bye. Thank you.
Bye. Thank you.